Hello guys, this is Dr. Satheesh Kumar from Department of CSC MLRITM. Today we are going to discuss how to solve XOR as well as XNOR problem using neural networks. So as we discussed in the previous lecture, a single layer perceptron is used to solve the linear problems only. But when we come to XOR problem as well as XNOR problem, these are non-linear problems. So single layer perceptron will not able to solve the problems which are related to non-linear category. So as we discussed, the activation function which is used to convert non-linear data into linear data, but that linear activation function will not be applicable for the XOR problem as well as XNOR problem. So for this, we need to introduce a non-linear activation function which is to be discussed today. Here, for example, in the case of XOR as well as XNOR, in both the cases, these inputs we are going to have is in non-linear category. For example, if we have two sets, the set A, let us assume we have input x1 as well as input x2. x1 is having the combination of 0 and 1 as input, and x2 also having the combination of 0 and 1. So there is a possibility, that is multiple combinations are there, 0 and 0, 0, 1, 1, 0, 1, 1. In the case of XOR, the simple logical gate is going to produce an output called, when both the inputs are different, it is going to produce the output as 1. When both the inputs are same, it is going to produce the output as 0. So in the case of 0 and 1, in the case of 1 and 0, we are going to get the positive output. In other cases, we are going to get the negative output. Now, here as we have 0 and 1, 0, non-linear data we are going to have. In the case of non-linear data, the single layer perceptron will not solve the resultant outcome. So for that, we need to introduce the multi-layer perceptron instead of using single layer perceptron. So just remember this logical gate. When both the inputs are different, we are going to produce the output of positive, that is 1. When both the inputs are different, we are going to get the result as negative, that is 0. So why fail? That is a problem here. As the mathematical representation of that activation function, here the step is the activation function, y is the output here, w is the weight, and x are the inputs, and then b is the bias. So if we consider the simple neural network which is having two inputs, for example, x1, x2 are the inputs here, and we are also going to have hidden layers. Let us assume two neurons we have in the hidden layer, that is H1 as well as H2. So in both the cases, in the input layer, we have two inputs. At the hidden layer, we have two neurons, H1 and H2, and we are going to get the output called Y. Now, if you want to process the data, these inputs are accepted by the hidden layer as well as these inputs are also accepted by the hidden layer. X1, X2 is passed as the input for the hidden layer, H1. And then x1, x2 are the same inputs which are transmitted to the hidden layer, that is second neuron called H2. Again, H1, H2 are processed to produce the output. Let us assume this is a single neural network structure to solve the XOR problem as well as XNOR problem. Just I want to recall this here. Y is the output, step is the activation function. Any activation function we can use. Either that may be single layer perceptron or multi-layer perceptron. That may be ReLU activation function. That may be sigmoid activation function, or that may be normal activation function which can be used to solve. In this activation function is used to convert the nonlinear data into linear format. That means if Wx plus b is the nonlinear data, we cannot solve this Wx plus b with single layer perceptron. For this, we need to introduce multi-layer perceptron so that this nonlinear data will be converted into linear format by the activation function. Now, after applying the activation function, if the predicted output is not same with the actual output, if both are not similar or both are not closer, in that case, we need to apply the back propagation mechanism. That is, when we come back to the previous layer, either to hidden layer or to input layer based on the variation between expected input and actual input, what we need to do is, we need to adjust the weights here. For every connection is going to have weight here. For every connection we have weight here. So these weights are to be updated here. By applying weight updation, again we'll process the same thing. We'll check the output again. If the predicted output and actual outputs are not closer, again we'll come back for the previous layer by applying back propagation. So for that, to overcome these problems, we are going to introduce the multi-layer perceptron to solve the XOR problem as well as XNOR problem. For that, what we are going to do? In this case, as we have the standard structure, input layer, hidden layer and output layer, as we are solving XOR problem or XNOR problem, how many hidden layers are required for this particular problem? In general, we have an input layer, we have a hidden layer and we have an output layer. Here, the number of neurons in this hidden layer and the number of hidden layers in that particular network are purely depend on how many features we are extracting. In this case, as the possibility if x1 and x2 are the inputs, for x1 we have a possibility of 0 and 1, for x2 also we have a possibility of 0 and 1. How many features we are extracting? 2 features we are extracting. That's why I am taking only one hidden layer with 2 neurons. So we are taking one hidden layer with 2 neurons because we are extracting 2 features from this particular neural network. So H1 is 1 neuron, H2 is 1 neuron in one particular hidden layer, and these are the inputs, number of inputs we can have. How many inputs we have? Either that may be 0, 0 or 0, 1 or 1, 0, 1, 1. So this is a combination of inputs. That means 2 input features we are going to insert into that corresponding architecture. So I am taking 2 inputs. 2 inputs, one hidden layer with 2 neurons, and it is going to produce the output. Either the output is 0 or the output is 1. Based on the activation function which we are using at the hidden layer, it is going to produce either 0 or 1. So let us how the data will be transformed from input layer to hidden layer and hidden layer to output layer. As per our discussion, we have three steps are there. In the first step, we have an input layer. In the second step, we have hidden layer, and the third step is output layer. Now, we accepted 2 inputs here. X1, X2 are transmitted to the hidden layer with 2 neurons, H1 and H2. And these 2 neurons are processed to produce the output here. Now, how this step-by-step process will be transformed from input layer to hidden layer to output layer, we'll discuss now. In the first step, the input to hidden layer transformation, how the inputs are transmitted to hidden layer to process the data. For example, as X1 and X2 are the inputs, H1, H2 are the hidden layers, and we are going to have the output called Y. Now, we have a connection between X1 and H1. We have a connection between X1 and H2 in the same manner, X2 to H1, X2 to H2. And now, we are going to have weights here. This weight will consider, for example, W11, and this weight we are considering from W12, and this weight is W21, and this weight is W22. In the same manner, H1 to Y1, this is second step. How whatever the output we have in H1, that will be transformed as an input for the output layer. Whatever the output we got for H2 will be transformed as an input for the second layer. For example, if this weight will consider W31 and this weight will consider W32. So to calculate the hidden layer, H1 neuron at the hidden layer, I am using the activation function called sigma. So this is activation function we are using, that is called sigmoid activation function. In general, normal activation function, if we use f of x activation function f of x equal to 1 if x value is greater than or equal to 0. If f of x equal to 0, otherwise. That means if x value is greater than or equal to 0, the output we are going to get is 1. That is the activation function. So to convert the nonlinear data into linear format, if x is greater than or equal to 0, the output of the activation function is 1. Otherwise, the output of the activation function is 0. In the same manner, if you apply sigmoid function, what is the activation function definition for sigmoid? In mathematics, we'll write 1 by 1 plus e power minus x. In this case, if f of x equal to 1, in the case of x greater than equal to 0.5, 0 otherwise. How you are defining x greater than equal to 0.5? That means if x value is greater than equal to 0.5, we are getting 1. How? For example, if x value is 0, 1 by 1 plus e power minus 0. So e power 0 is 1, 1 plus 1, 2, which is equal to 1 by 2, that is 0.5. That means if x value is 0, we are going to get 0.5. We should not we should not calculate the activation function with the negative values. So the minimum input value is 0. That's why I'm writing x greater than equal to 0.5. We are going to get the output as 1 here. And if x value is less than 0.5, we are going to get the output as 0. So this is the activation function definition for non-linear as well as linear or single-layer perceptron or multi-layer perceptron. Now, if we can apply here any activation function, either normal one or the sigmoid activation function, or ReLU also we can use. But in the next example, we'll try to discuss the ReLU activation function. Now, so we'll solve the same problem with the help of normal activation function and with the help of sigmoid activation function to show the normal function will not solve the nonlinear data. The sigmoid activation function will solve efficiently when we have nonlinear data. That I will try to show. So here, sigma I am specifying either to specify the activation function normal or the sigmoid, or you can also use ReLU to solve that particular problem in the first step. Second step, hidden layer to output transmission. So once the outputs are transformed at the hidden layer, these outputs are transmitted as the input for the second layer. Now, here the problem is we are going to introduce one bias at each and every weight. For x1, we are going to have some bias. x2, we are going to have some bias. And also h1, h2, y also we are going to have some bias. That means there is some deviation from expected input as well as the actual input. For that, we are going to introduce some bias. Now, whenever the expected output and whatever the output we are expecting here, if it is not closer to the actual output, what we need to do is we need to come back. That's why in the second step, hidden layer to the output transmission, what we will check is, again we are going to apply the same function, either the normal activation function or the sigmoid activation function or the ReLU activation function we are going to use to transform the nonlinear data into linear data. So that is in the second step. Third step, what we are going to do is learning weights from biases. This is the beauty of neural network here. Whenever the weights are applied for a particular network, so it is going to extract the features by learning the weights. So by understanding the weights of these connections, it is going to learn from the particular weights as well as biases. So the weights and biases are used to train the network. Now, once it is learning the features from weights and biases, now the network, whatever the network we designed, that may be ANN, that may be CNN, that may be RNN, these networks are ready to train the data or train the features. Now, in the fourth step, we are going to train the model to solve XOR problem. So what are the combinations of inputs? What are the weights we are going to have? And what are the number of neurons at the hidden layer? As well as how many possible outcomes we are going to get. So this sort of training will be applied once the network is ready by learning the features from weights as well as biases. So these are the 4-step process. In the first step, how the input will be transformed into hidden layer. Second step, how the hidden layer will be transformed into output layer. And the third step, how the weights and biases are used to learn the features. And in the fourth step, the training will be done. So once the training will be done, the model is ready to extract the features from the input. So we'll try to give multiple inputs. we'll try to produce or we'll try to provide multiple combinations of inputs. If we have two inputs in the case of XOR, as I said now, the various combinations are 0, 0, 0, 1, 1, 0, 1, 1. Like this, we'll try to give four combinations of inputs and we'll try to train the model. So once the model is trained, then whatever the inputs we given with different weights, so it is going to produce the accurate output after the successful training. Now, so let us take one example here to solve the XOR problem. So I am taking random weights here, W11 equal to 1, W12 equal to 1, bias is 0.5 I am taking. Second case, W211, W221. So if we construct the simple network, the inputs are X1, X2, hidden layer, 2 neurons, Y. So these weights I am defining here. W11 is 1 here. W12 is also 1, this one. And W21, X12, H2, the weight is 1. W22, X21, X22, H2, the weight is also 1 here. So these are the weights here. Now, if you apply the function summation of Wi xi plus b. So in the case of I and j, I am writing W11 plus x1, W11 into x1, W12 into x2. This will become the definition of H1. In the case of H2, W21 into x1 plus W22 into x2. This will become the H2. So by using this formula, we can get the value of H1 and H2. In the same manner, from H1 to Y, this is W31, this is W32. How you are going to calculate Y here? Y equal to W31 into H1 plus W32 into H2. So by calculating this, we are going to get the value of Y. That is, Y is the output here. Based on the output, we are going to apply the activation function. So that means we are going to get f of Y. So for example, here, all values 1 I am taking. First bias I am taking 0.5. Second bias I am taking minus 1.5 for example. In the same manner. So I am going to calculate H1 here. How we are going to get H1? W11 into X1. What is W11? 1. What is X1? 0. So 1 into 0 plus W12 into X2. X2 is also 0. So 1 into 0 plus 1 into 0 plus B. What is bias? 0.5. So 1 into 0, 0. 1 into 0, 0. 0 plus 0 plus 0.5. F of 0.5. So in the case of normal activation function, how we define f of x equal to 1 if x greater than equal to 0. Otherwise, we are going to get the output as 0. So here, f of 0.5, that is which is greater than 0.0. So we will get f of 0.5, that is which is greater than 0. We are going to get the 1 as the output here. In the same manner, for H2 also, 1 into 0 plus 1 into 0 minus 0.5. Bias is minus 0.5. So you are getting f of minus 0.5, which is less than 0. So you are getting the output as 0. Now, we'll try to calculate y here. W31 into H1 plus W32 into H2. We are going to calculate. So W31 is 1, W32 is 1, and bias is minus 1. If you apply this, 1 into 0 plus 1 into 0 plus 0.5. Sorry. Why we need to calculate here? W31, 1 into H1. What is H1? 1 plus W22, 1 into H2. What is H2? 0 minus 1. 1 into 1, 1 plus 1 into 0, 0 minus 1. 1 plus 0 minus 1, which is equal to 0. So the output of y equal to 0 we got here. The output of y equal to 0 we got. Okay. So now, as per the table, when we got 0, 0, which is equal to 0, When we got 0, 1, we got 1, 1, 0, 1 and 1, 1, 0. So this is a table, we have XOR table, and whatever the inputs we given 0, 0, whatever the output we got is 0. Now our actual output is 0 and resultant output is also 0. Both are matched here. So we can solve the problem when the inputs are 0, 0. Now let us try to modify the bias here. So I am taking bias as 0.5 here again. So if we take 0.5, what is the output we are going to get here? 1 into 0 plus 1 into 0 plus 0.5 f of 0.5. If f of 0.5 means the output we are going to get is 1. The actual output is 0. Resultant output is 1, which are not matching. That means what? For all the biases, this problem may not be solved in normal activation function. Now we can also try 1, 0, x1 equal to 1, x2 equal to 0. Then x1 equal to 0, x2 equal to 1. Then x1 equal to 1, x2 equal to 1. In all combinations we can try and we can check whether the actual output as well as the resultant output is same or not. If not, we can say this particular problem, XOR as well as XNOR problems, cannot be solved with the normal activation function. If we use the same example, I'll try to calculate with the sigmoid activation function, for example. In this case, so I'm using sigmoid activation function. So I'm taking x1 equal to 0, x2 equal to 0. Same process I'm following here. So the sigmoid activation function definition is 1 by 1 plus e power minus x. So this is a formula I'm going to use here. So same 1 into 0, sigmoid of 0.5. That means what? 1 by 1 plus e power minus 0.5. So we are going to use the logarithmic table or calculator, scientific calculator we are going to use to calculate the value. The value we are going to get is 0.622. In the same manner, H2 we are going to get is 0.182. Y we are going to use 0 minus 0.196, which is equal to 0.451. Now, Y is the output here. H1, H2 are the neurons at the hidden layer. So Y of 0.451. As per the sigmoid activation function, f of x equal to 1 if x value greater than equal to 0.5. F of x equal to 0 otherwise. So here we got 0.451, which is less than 0.5. So f of x equal to 0. So we are going to get the 0. The actual output 0, 0. The output is 0. So we are also getting the output as 0. The actual output is 0. The resulting output is 0. So we can say we can solve the problem with this. Now let us try to modify this particular bias here. By changing the bias, again we'll calculate the sigmoid activation function. Let us see whether that particular value is matching or not. Likewise, here also we are going to give inputs 0, 0, 1, 0, 0, 1, 1, 1. 4 combinations of inputs we are going to produce, and let us check the actual value and predicted value are same or not. If both are same, we can solve the problem of XOR as well as XNOR. In the same manner, like how we are calculating XNOR for 4 combinations 0, 0, 1, 0, 0, 1, 1, 1. In the same manner, we are going to calculate the problem of XNOR. What is XNOR here? The same process we are going to use for XNOR also, but in the case of XOR 0, 0, 0 we are getting, 1, 0, 1, 0, 1, 1, 1, 1, 0 we are getting. In the case of XNOR, when both the inputs are same, we are going to get the output as 1. When both the inputs are 0, we are going to get the output as, when both the inputs are same, we are getting 1. When both the inputs are not same, different, then we are going to get the 0. So the same combination we can apply for XNOR also. In the case of, we can simply conclude that in the case of XOR as well as XNOR, we are going to solve the nonlinear problems with the help of neural network by using multi-layer perceptron. Multi-layer perceptron. Other than this, if we have linear data, then we are going to use single layer perceptron. So XOR problems, XNOR problems may not be solved with the help of single layer perceptron, but the same can be achieved with the help of multi-layer perceptron. So I hope you got the difference between single layer and multi-layer perceptron. Thank you.